So, hydrohalogenation is the addition of a hydrogen and a halogen across the double bond of an alkene. It's an addition reaction since we're adding elements to a molecule that weren't there before and we're not removing any elements. In this case, we can use HCl, HBr, or HI. Any of those three halo acids will make this reaction happen. There is a regiochemistry for this reaction, which is that it undergoes Markovnikov addition. That means that the halogen, the non-hydrogen group, will add to the more highly substituted carbon. And in this case, there is no stereochemical preference. So we'll go through an example with a mechanism, and we'll pick an example where we have an asymmetric alkene. So notice that the double bond on one side has a substituent, or is more substituted than it is on the other side. And we'll start using simply HCl. So as we begin our mechanism, we want to draw out all the elements where the action is happening. And we start by protonation of the alkene bond to form a carbocation intermediate. So the pi bond breaks, reaches out and grabs the hydrogen. This is going to connect the hydrogen to one of the two carbons in the alkene. This breaks the HCl bond, and those electrons go with the chlorine. So in this case, first step in any mechanism involving a strong acid, the acid is doing its acid thing. Acids are proton donors. And the alkene is acting as the base, and bases, of course, are proton acceptors. After this step, we are forming a carbocation, and we have a choice of where to put the hydrogen that we have just taken from the HCl. And we want to put that hydrogen on the carbon, or we want to place that hydrogen such that we get the best possible carbocation. So notice right now these two carbons both lack a third bond. Either one of them, or fourth bond, excuse me, either one of them could be the carbocation. This would be secondary, this would be primary. More highly substituted is more stable for carbocations, radicals, and alkenes. And resonance is even better. So the secondary carbocation will be the better place, or the better carbocation to form. In order to do that, we put the new hydrogen on the primary carbon. That creates the carbocation. We have also created a chloride anion. And the chloride will then act as the nucleophile. So you notice that this last step is the same last step that we have in SN2 substitution. And the chloride simply attaches to the carbocation. The carbocation, of course, is trigonal planar. And so regardless of where this hydrogen is, that chloride has two possible directions from which it could approach. There's now free rotation around this middle bond, and so the chloride is not adding with any specific stereochemical relationship to the original hydrogen, and thus we say this reaction is not stereospecific, or that it has no stereochemistry. It does, however, have the anti-Markovnikov regiochemistry, which is to say that it has Markovnikov regiochemistry, which is to say that the non-hydrogen group goes at the more highly substituted carbon, and the hydrogen that was added goes to the less substituted carbon, or, another way to look at it, the hydrogen that's added goes where there's more hydrogens. It's like they're having a little party. And we have the non-hydrogen group, the nucleophile, in this case the chloride, adds to the more substituted carbon because that was the more highly substituted and therefore more stable and therefore more easily formed carbocation.